Okay, so now let us get to chapter 4. Okay, chapter 4 basically is we will talk about exponential functions, and later on in the chapter we will talk about logarithmic functions. Okay, okay, so then let's see about the exponential first. Okay, so exponential functions, we have a growth or decay model. Okay, it's a function that growth or shrinks at a constant percentage rate, growth rate. Okay, the equation can be written in the form y equal to f of x equal to a times b to the x, or f of x equal to a times 1 plus r to the x, where b equal to 1 plus r. Now, in other words, if I want to solve for r, meaning basically r equal to b minus 1 then, right? Okay. B must be positive and b cannot be 1. So therefore, again, when you work with exponential function, remember this, the base b to the x, this base right here, must be positive and then cannot be equal to 1, because again, you know that 1 raised to any power is just 1, right? Meaning if b equal to 1, basically the function is a constant function then. Then let us learn some terminology here. Is that a is a coefficient, the initial or the starting values of the functions. So why we call it initial? One thing about this is, if x equal to 0, then you will see that f of 0 is a times b to the power of 0. And then we learn that b to the power of 0 is 1, so which is actually just a. So therefore, in this case right here, you will see that when x equal to 0, we have a. So this is the reason that we call this the initial value then, or the starting values. Now, look at this. When x equal to 0, basically what we have here is we also have the y-intercept, right? So basically a is the y-intercept as well. Okay? R is a percent growth rate if R is positive, decay rate, R is negative. And then B is, we call the growth factor if B is greater than 1, decay factor if B is between 0 and 1. Okay, so let's see how everything is actually worked out together. So let us look it back to the section 4.0. Okay, now remember this section 4.0 basically is talk about the exponent property. It's just the review. Make sure that you actually work on this handout. Okay, know all the 8 properties, especially we know that if it is raised to the power of 0 is 1, how do we actually take care of the negative exponents? And later on in the later sections, in section property 4.3, then you also need to know the n root, okay? How do we actually rewrite, okay, into the exponents then? Okay, so now to this handout 4.0, we actually at the last problem, the last example is talk about how do we actually graph the exponential functions. Okay, now again, I talk about f of x is equal to a times b to the x. Okay, where a is the initial values of the y-intercept, b is the base, right? It is related to kind of like the exponential growth for decay. Okay. Okay, so then now let's see. Now to this example right here, I have f of x equal to 2 to the x. Then from here, what I would like to do, I would like you to try to identify what is a, what is b. Okay. Okay, so then now let's check it out. Okay, so if I have 2 to the x, basically it's kind of like it means that I have 1 times 2 to the x. So therefore, in this case, oh, actually a is equal to 1 and b must be 2 then. Okay. Then we know that b is equal to 1 plus r. In other words, r is equal to b minus 1. So therefore, in this case, r basically is 2 minus 1, which is 1. Okay, so now how is everything related? Okay, now first of all, let us check out the table here. Do you see that if you have, again, from 0 to 1, when the input x is increasing by 1 unit, what happened to the y? Y basically is double the y. From 1 to 2, then again, you double it again. And then from 2 to 3, 4 times 2, right? This is one thing about this is actually related to your b values right away, okay? And then now, let us look at what is R then. R is what we call the growth weight, okay? If it is a weight, that means what? If I want to rewrite 1 into percentage, then we know that 1 equal to 100%. Okay. Then now, let's see. Do you see that when I have from 1 to 2, I increase it by 1 unit. But what is the percentage that increase? Is actually is increased by 100%. Same thing, from 2 to 4, we increase it by 2 units, right? 2 over 2 is 100. So again, you will see that I increase it by 100%. And then 4 to 8, again, we increase it by 100%. So therefore, in this case, it actually is this relation right here is actually to tell us how we find the R, okay? Okay. Then now, how about if I have 1/2 to the x, okay? So same thing. What I would like you to do is I would like you to find out what is A, what is B, okay? And of course, I would like you to actually try to find what is R as well then. Okay? Then, of course, to this one right here, we know that A is 1, B basically is the 1/2, right? Then, in this case, then what is R? R is equal to B minus 1, so which is, again, negative 1/2 or negative 50%. Then, again, do you see that? From 8 to 4, is actually, it is decreased by, again, is decreased by 4 units. 4 is half of the 8, right? Which is decreased by 50%. From 4 to 2, again, is decreased by 2 units. 2 is, again, is half of the 4. Okay. So again, this is actually is related to your R. Okay. Okay. I hope that in this case you I hope that you found the relationship between the B and the R. Okay. Okay. And now let us go back to the section 4.1 now. Okay. Then once we know this, then let's see how do we actually graph this. Okay. Okay. Now remember 2 to the x. The graph of 2 to the x basically is just like this. Okay. And then the graph of 1/2 to the x power 1/2 to the x. Okay. And one thing that is from, oh, I forgot to talk about a, yeah. Do you see that to this one, basically to the 2 to the x, the y-intercept is 1, and 2 to the x, 1/2 to the x, again, the y-intercept is 1. Because this one right here is related to the a values, okay? It's the initial value. Anyway, then now, if a is positive, and then b is greater than 1, do you see that the function is increasing? And then, of course, to this one right here, the y-intercept, it must be a, the initial value. So therefore, again, the range is from 0 to infinity. Okay? On the other hand, when b is between 0 and 1, just like 1/2 here, the function is decreasing. Again, if a is positive, then now the function is decreasing when when b is between 0 and 1. Okay. But one thing about this is what happened to the range. The range is still from 0 to infinity. Okay? And now, keep the same. If I want to find b is greater than 1, but right now a is a negative. So then, in this case, if you remember the transformations, if a is negative, basically what happened here is we have the graph that is reflecting about the x-axis then. So we could look at this graph right here, okay? And then we could actually graph this. Then of course, this one right here is still a. Now remember, this a value is a negative values, right? Because a is less than 0. Okay? And now, do you see that from left to right, the function is going down, so meaning the function is decreasing now. And how about the range? The range is from negative infinity to 0, okay? Okay, so now it is your turn. Now go ahead and try to finish the table, okay? Okay, and now let's try this. So to b is between 0 and 1, that means we are going to work with this graph right here, okay? But again, a is negative. This is x, this is y, this is 0 right here. So therefore, again, we have a reflection about the x-axis. That means the graph basically is increasing, right? Again, remember this, the y-intercept is a. And of course, what happened to the range is from negative infinity to 0. Okay, so then, now if you look at the graph of exponential functions, then you will see that what happened to the domain is all real number. There's no x-intercept. The y-intercept is always 0a, right? The initial values. And then we have a horizontal asymptotes at y equal to 0. Then you will see that to the functions. Basically, the function is one-to-one functions, meaning we should be able to find its inverse now, okay? And then to be, that's mean, in fact, the inverse functions of exponential function is logarithmic functions, which is we will introduce in section 4.3. Okay. Okay. And now let us try to learn the terminology of what about the exponential function now. Okay. So to this one right here, f of x equal to 100 times 1.08 raised to the power of x. Now, one thing about this is, now remember, we cannot multiply 100 to 1.08 right away. The reason is we have to follow the order operations. We have to take care of the power first before we take care of the multiplication, right? So therefore, again, make sure that you are not multiply 100 to 1.08, okay? Okay, so what I would like to do here is, I would like to write down, again, f of x equal to ab to the x, right? Then, in this case, to this problem right here, what is a, what is b, okay? And then what is r? Think about this. Yes, okay, so a is 100, good. B is 1.08, and then what is R? Remember, R basically is B minus 1, right? So I will have 1.08 minus 1, which is 0.08, okay? Or it's just 8% then. Okay, so then now, let's see, how do we actually work out this problem? Then, now remember, what is the initial value? A is the initial value. And then in this case right here, because the b value is greater than 1, meaning we have a go factor. And of course, this one right here is related to b values. And then have a percent go factor in this case right here, meaning this is related to r. And of course, we know that the y-intercept is related to a, okay? So basically, for this problem right here, my initial value is 100. my growth factor is 1.08, and then my growth weight is 8%, okay? Or sometimes we just write down 0.08, and then my y-intercept. So how about I write down as a 0.0100. And then in this case, you will see that what happened here is A is positive, B is greater than 1. Basically, the function is increasing. Right? And then, of course, the y-intercept is 100 here. Okay, so then we could actually sketch the function. Okay? Okay, so now it is your turn. Now go ahead and try B. Now B is, I have g of x equal to negative 4 raised to the power of negative x. Okay. So again, if you don't know how to take out the negative exponents, make sure that you go back to the 4.0, right? The review. Okay. Okay. And now let's see how do we actually do this one. Then now before I do this, I would like to rewrite this into something like this. Okay. Again, you know that negative 1 times x is negative x. Okay. Then, if you know, then what we could do here is, remember x to the negative 1. Oh, I'm sorry, this is 4 right here. No, my bad. So it will be 4 to the negative 1 basically is 1/4, right? Okay. Then now, you should be able to answer the question now, because again, in this case, what is A, what is B, and then what is R, right? So based on this, we know that A is equal to negative 1. B is 1/4. R is 1/4 minus 1, which is negative 3/4. Okay, and now, so again, I know that my initial value is negative 1. And then remember the base. What is the base? The base is B. Okay. Then B is 1/4. And then the R value basically is negative 3/4. Okay. Or negative 0.75. Or negative 75%. Okay. Then of course my y-intercept is 0, negative 1, right? Okay. Then now remember this one A is negative, and basically 1/4 meaning the function is decreasing, and then the negative meaning what we flip this. Okay, then now we know that this number right here is negative 1, the y-intercept. This is x, this is y, this is 0 right here. Okay, yeah, that's it. So this is how we sketch, okay, the exponential function based on the a values and the b values. Okay, so now then let's look at this. A population of 1,000 is decreasing 3% each year. We would like to find the population in 30 years. Okay. Now, first of all, how do I know that this function right here is exponential functions? Because we have a constant decreasing weight, okay, per year. That means this basically is related to the R values then. So then let's see. Now remember when we work with the exponential function, we actually will have f of t equal to a times b to the t, or a times 1 plus r raised to the power of t. So in this case, I will use this one to set up my problem. The reason is, from the problem, I already know that my r values. Okay? So then now let's try this. So first of all, I have some givens. The givens is a population of 1,000, meaning what this 1,000 right here is my initial value. So I have a equal to 1,000. Decreasing by decreasing 3% each year. This is related to the percentage. So I know that R will be negative 3% or negative 0.03. Then. Okay, then now maybe let us try to work out the problem now. So I will have f of t equal to 1,000 1 minus 0.03 raised to the power of t. Then if I simplify, it will be 1000.97 t. Okay. So then now you will see that what do we just have? We just have the function. Okay. And now to this one right here, let's see how do we actually sketch the functions. Okay. This is t right here, is time. And then this will be the population. Okay, then now we know that what happened to the population. We start at 1,000. Okay, and then now we are going down by 3% per year. Now you will see that to this one right here, I don't have any data to the left of x y equal to 0 this line, right? X equal to 0, t equal to 0 this line. The reason is it doesn't make sense that we have any data before the starting time, right? A population of 1,000. So we know that here, 1,000. And then now the function is decreasing. The reason is this number right here is actually less than 1. Okay, and now what I would like to do is I would like to find that in 30 years, okay, then what is my population? Okay. So basically, in this case right here, I just need to evaluate f of 30. So I will have 1,000.97 raised to the power of 30. Then if you use your calculator, you should be able to get your answer is 401. Now again, you may have a lot of decimal. Remember, this is a population, right? Human being. You cannot have 0.5, 0.2, something like this. So you have to round it either up or down, right? To make it a unit. Then now the answer will be what? Therefore, the population will be 401 in 30 years. Okay. Okay, so now it's your turn to work on number 4. So it said that right here, the population of Egypt has been growth at a rate of 1.68% per year. Again, exponential function. In 2008, the population of Egypt was about 81.7 million. So to this one right here, first, we do not have any natural initial values. Okay, we don't have an initial values. However, we know that in 2008, the population is 81.7. So what I would like to do here is I would like to work with this year, 2008, and then make this year the initial value. How could I do this? Here, we just need to work with a statement then. I could write down let t be the year since 2008. Okay, so what does this mean? It means that when t equal to 0, it is corresponding to the year 2008 then. Okay, so therefore again, this statement right here is really important, okay, to do this problem. Then now, once I set up that, that's mean again, I use the 2008 to be my initial values. That's mean in this case right here, my initial value will be 81.7, right, million. And then my R is, again, 1.68%. Then we know that this one is 0.0168. Then, of course, the function that I will have f of t. Oh, since this is related to the population, how about I use p of t then? P of t is 81.7 times 1 plus 0.0168 t, or P of t 81.7, 1.0168 t. Okay. And again, this is actually my functions. Okay, then now I would like to estimate Egypt's population in 2020. So in this case right here, we know that 2020, which is 12 years after 2008. So therefore we know that is t equal to 12. So what I need to do, basically I just need to evaluate p of 12, 81.7, 1.0168 raised to the power of 12. Okay. And then you got the answer, which is 99.8 million. So then in this case, we could say that in 2020, the population will be 99.8 million. Okay, now there is one thing that I would like to talk about. Okay, so is how about the graph that we have? Okay, so should I start the graph is from here? Okay, from y equal to from x equal to t equal to 0. Okay, of course in this case right here is upright because it's increasing. Should I start it from 0 or should I extend it to the other side? Now in this case, I could extend it to the other side, meaning what? When t equal to -1, it still means it is 2007 then, right? So therefore, again, when the time is -1, -2, in this case, it makes sense to have time equal to -1 and -2 and so on and so forth. However, it doesn't make sense to the example number 3. Okay, so therefore we could do it this way. So this is the population. And this is your t. Okay. Now, before I move on, there's one question that I would like to ask you. Do you know the difference between, okay, let me ask you. Do you know the difference between 81.7 million and 81,700 million? Oh, 1,000, okay. Are they the same or they're different? Okay. Actually, they are not the same. Now, what is the difference between them? This one is the exact amount. What does this mean? It means that if I write 81,700,000, it means 81,700,000. Okay, 81 million. However, if I write 81.7 million, then in this case right here, it could mean that is 81,726,349. Okay. This is actually is the idea about the difference between 81.7 million and 81,700,000. This is the approximation. This is the exact. Okay. So therefore, again, when you work with the problem that I just showed, when the problem talk about just 81.7 million, then you just use 81.7. Okay. And you just state the unit is a million. Then. Just like this. Okay. Okay. Okay, then now let us work on the next two problems. The next two problem is really helpful because again, when you get to the section 4.6, then you will see that we will have some problem like this again. Okay. So right now I have given 2 points, 1, 3, and 2, 2 and 4.5. Okay. And then I would like to find the equation of exponential functions that pass through these 2 points. Okay. So first of all, we know that the exponential function must be at the form f of x equal to a times b to the x. Okay, so this is what we know. And then let's see how do we actually work out the problem. Now to this problem right here, we have 2 points. Okay, and then I have the point. It is 1, 3. And then we also have another point is 2, 4.5. Okay, and then now I know that this is the exponential functions. Okay, I actually have a function that just go for these 2 points right here. Then now, how do we actually work out, okay, this problem here? No. Let me write this. This is 2, 4.5. Okay. Then we have to go back to our really first section 1.1. We know that 1, 3, basically it is what is f of 1 equal to 3, right? The input is 1, the output is 3. And same thing with 2 and 4.5, is mean that f of 2 equal to 4.5. Okay. Then now look back to this problem. If I have f of x equal to ab to the x, so to this equation right here, or functions, how many unknowns? We have 2 unknowns. If you have 2 unknowns, basically what you need to do is you have to set up 2 equations to solve for the 2 unknowns. Okay, so this is the idea about system of equations then. Then how do I create the 2 equations? Basically, we are going to use the 2 points right here to help us to set it up. So then we know that f of 1 is a times b to the 1 power equal to 3, right? And then we also know that f of 2 is ab to the square equal to 4.5, okay? And this is how we set up the 2 equations using the 2 points, okay? And then now, what I would like to do is, I would like to solve the 2 equations then. Now the technique is actually here, okay? So the first step, step number 1, is actually I would like to solve for a. And then step number 2, we would like to solve for b then. So this is actually the idea. We solve for a first, and then we solve for b. Okay. And now use the substitutions then. Let's see how do we actually do this. Okay. So again, when I write down E1, E2, meaning equation number 1 and equation number 2. So from equation number 1, then we have a times b to the a times b equal to 3. And now remember the first step is we solve for a. So I will have a is equal to 3 over b then. Then now I call this equation number 3. Okay. Then now, what do I need to do next? I'm going to substitute a equal to 3 over b in E2. Okay. We use E1 to solve for a, then we plug it in a to E2. Then I will have 3 over b times b squared is equal to 4.5. Okay, this is what we have. And of course, in this case, you will see that b and b squared, they cancel it. So now I have 3b is 4.5. And now b will be 4.5 divided by 3, which is 1.5 then. Okay. Now, after we find b, then what do? We are going to substitute b equal to 1.5 in, maybe we could plug it in E3. Okay. Then I have a equal to 3 over 1.5, which is 2. Then now, what we could do? we could actually check the answer now. Check if A equal to 2, B equal to 1.5. We would like to check with maybe E2 then. Then I will have 2 times 1.5 to the square. Is this equal to 4.5? Okay. And then now we know that 1.5 to the square is 2.25. And once we multiply 2, then we have 4.5 equal to 4.5. Okay. So therefore, in this case, we know that f of x is a is 2, b is 1.5 to the x. Okay, so this is exactly how we find the exponential functions from 2 points. Okay, of course, right now to number 6, this is your turn, right? Now try to do the problem now. Okay, so you could actually keep the example number 5, okay, and then check out how do you actually work on number 6 now. Okay, so then first I have p of t is ab to the t. And then now you could using a point f of 2, p of 2. The output is 400, right? It is a times b to the square equal to 400. And then the next point is 4 and 256. So we have p of 4 is a times b to the 4 is 256. And of course, we have this is E1, this is E2, right? Equation number 1 and equation number 2. Okay, then remember again, what do we do first? We would like to solve for A first. Then I have this one right here. It will be A times B squared equal to 400. Okay, so again, I start with E1. Then A is 400 over B squared. Okay, then now the next step is we would like to again solve for B then, right? Okay, so how do we solve for B? Then we could substitute A equal to 400 over B squared in E2. Then now I have 400 over B squared times B to the 4th is 256. Then of course this one and this one cancel. Okay. Then we will have 400 B squared equal to 256, or B squared equal to 256 over 400. And now we could take the square root both sides of the equation. Okay. Now, one thing about this is if you take the square root to both sides of the equation, you should have plus or minus. But remember, b is always greater than 0. Okay. So therefore, in this case, I don't need to again, I don't need to put plus or minus here then. Then of course, we know that the square root of 256 is 16. Oh, it's actually, if I use the calculator, I will find out that this is 4 over 5. Okay. Then, now, if we have this one right here, then after we find B, then what do? We could use the B to find A now. then we could substitute b equal to 4/5 in, maybe I call this E3, okay? In E3. Okay, then now I will have A equal to 400 over 4/5 to the square. Okay. Now remember, if we have this, that means we have A is 400 over 16 over 25, right? And you have to understand that this line right here is mean divide. So I will have 400 divided by 16 over 25, or I have 400 times 25 over 16. Right? And then now we could actually do this to simplify it. 4 times 4 is 26. 4 is 100 times to get 400. And then 4 and 100 is 25 times. So basically I have 625 then. Okay. And now you could actually check our solution now. Check if A equal to 625 and B equal to 4/5. We check with about E1, right? Then I will have, again, 625 times 4/5 to the square. Is this equal to 400? Then I will have 625, 16 over 25. And we know that 25 times 25 is 625. And then if you use your calculator, 25 times 16 is equal to 400. So therefore, in this case, I have A equal to 625 and B equal to 4/5. So therefore, I have P of T is 625, 4/5 to the T. So again, remember to work with the system of equations. First, you solve for A, then B. Okay. After we find B, then you plug it in to find A. Okay, so then now let us try to work with the application part of the exponential functions. One of the application is a compound interest. Okay. Now the compound interest formula is A of t is equal to A times 1 plus R over K raised to the power of KT. And where A of t is the account values after t years, sometimes we call it the future values. And t is measured in years always. So therefore, if the problem tells you that I have 18 months, meaning what, you have to convert into 1.5 years, okay, to plug it into for t. A is the starting amount of the account. We call the principal, or sometimes we call the investment. R is the annual percent rate. We call it the nominal rate. Okay, and K is the number of compounding periods in 1 year. So then let's see. How do I find K from the problem? Now you see that to this one, interest compounded weekly, right? So this is actually tell you that what K is, okay? So if I have compounded annually, meaning what, I calculate the interest once per year, so K is equal to 1. Semi-annually, meaning I calculate the interest twice per year, so K is 2. Of course, quarterly will be 4, monthly 12. I don't know if you know how many weeks per year. It's not 48, is actually is 52. Okay, kind of odd, right? Huh? But again, how about daily? 365 then. Okay, so how do I actually work with the compound interest formula? It's actually from the problem if you see compounded weekly. This is actually is related to the compound interest right away. So then let's see how do we actually set up the problem. So an investment, 150,000. So in this case, right away, I know that I have a given values. A is 150,000. Right? It's put in an account paying 6.5% annual interest. So to this one right here, basically this is my APR, right? Is my nominal rate. So my R is equal to 6.5%, or I convert it into decimal, 0.065. Okay. And then now it's compounded weekly. So therefore, in this case, it means that K must be 52. I would like to find the balance of the account after 4 years. So in this case, I know that T is equal to 4 years. What I'm looking for, I would like to find A of 4. Right? This actually is the idea here. Okay. Then now, let's see. First of all, I would like to set up the problem. So I have A of T is equal to 150,000 multiplied to 1 plus R, which is 0.065, divided by 52, K, raised to the power of 52 T. Then. And now, if I want to evaluate L of 4, then I will have 150,000, 1 plus 0.065 over 52, raised to the power of 52 times 4. Okay. Okay, so then now let's use a calculator, okay? Okay, so then now to this one, what I need to do here is go to the home screen, okay? Then I type it in 150,000, put a parenthesis, 1 plus 0.065 divided by 52. And then raised to the power of 52 times 4. Then I found out that the amount is 194,507.93. I round it to 2 decimal places. Okay, so usually we round it to 2 decimal places. Okay. Okay, then now the last one is, what is the total interest? Okay. And then remember, how do we find the total interest? It actually is the future values minus the principal, right? Okay. So therefore, in this case right here, we will have the interest is equal to 194,507.93 minus 150,000. So which is 44,507.93. Okay, so now it is your turn to work on number 8. Okay. So I have given the investment is $1, paying the account is 6%, and then it's compounded monthly. So K is equal to 12, right? And then I would like to find the balance of the account after 1 year. So I have T is equal to 1, and then we are looking for A of 1 then, and also the total interest. And now I have A of T is 1 times 1 plus 0.06 over 12 raised to the power of 12 times T, right? And now I have A of 1. And if you use your calculator, you actually will find out that it's 1.0616778112. Okay. Now I write down more digits, so then you will see that to the next example, then I use the number here. Okay. Then of course, how about my total interest? Is actually will be 1.0616778112 minus 1. Okay. Okay, now this number right here basically is tell you that the actual percentage yield that you have. What does this mean? It means that if you put in $1 at the beginning, after 1 year, then you will have 6 cents, right? How about if you put down $10, then you will have 61 cents. And then if you put down $100, then you will have $6.17, and so on and so forth. So it's kind of like a ratio here. So therefore, in this case, this is actually kind of like telling you the percentage that you earn over 1 year if you put it in this account right here. Okay. This is actually is the idea about the annual percentage yield. Then the annual percentage yield is the actual percent a quantity increase in 1 year. This can be calculated as APY. The annual percentage yield is 1 plus R over K raised to the power K minus 1. You will see that it's just like this, okay? So we set, again, if you remember the A of T here, then it's A times 1 plus R over K raised to the power KT, right? You will see that when I try to find the APY, what happened to A? A is 1, T is 1, okay? And then we minus the $1 that we invest, then you will get the percentage back then. Okay, so then now it is your turn. Now go ahead and try to fill this table. So we work on the 12 already. So I have the monthly K is equal to 12. And then what is the APY? It is 1 plus 0.06 over 12 raised to the power of 12 minus 1, right? And then, of course, in this case, you will see that the percentage, okay, I round it 3 decimal places for the percentage, is, again, to this one, it will be 6.168%, right? Okay, so then let us finish this table then. Okay, so now one thing that I hope that you notice, the bank pay you 6% per year, okay? However, the return is actually depend on how often that you calculate the interest. The more often that you calculate the interest, the return is better. Do you see that? 6%, 6.09, 6.136. When the K is 12, then I have 6.168. But K is 365, then I earn more. Okay. So this is actually is the idea about the compound interest. Okay. You earn the interest from the interest. And I hope that you know why we call this the R is the nominal rate, because again, nominal meaning just a name. So therefore, again, 6% per year. This is just tell you that it's just kind of like the name, but the actual earning may be different, right? Okay. Okay. Then now, before we move on, I would like to introduce another numbers. Okay, we call it the Euler numbers, or sometimes we call it the natural number E. Okay. Now, E is a number. E is a letter used to represent the values that 1 plus 1 over k raised to k power. Suppose as k get big. So you will see that to this table. When k is 1, 1 plus 1 over k raised to k is 2. When k is increased, do you see that the number is getting bigger? But one thing about this is the number is not getting bigger and bigger to infinity. However, the number is getting bigger and bigger toward a number, okay? So therefore, again, this number right here is actually is what we, because it's, again, we use it a lot, so therefore we use a symbol to represent this number, okay? So we use the E to represent this number. Okay, so now how do we actually evaluate e to the power of 3 or e to the power of negative 0.53? Then let us go back to your calculator now. Now you will see that on your calculator where you could find e. Okay, so you could, again, you could use second and divide, okay, to bring e, and then you put enter. Then this is actually is the number e, just like pi, okay? It's just a number. Then, now usually we will use this one is the second and the ln. You will bring up e to the power, okay? So if you have e to the power 1, of course, this is just e. And if you want to evaluate e to the power of 3, so second ln, right? Bring up the e to the power now. So we type in 3, okay? And of course, we could have this one raised to the power of negative, right? Now notice the number that we have, the output is always positive, okay? No matter the power is positive or negative, your values is always positive, okay? Then let us try to run it to 5 decimal places, right? So then I have, so I have e to the 3 is 20.08554, and then e to the negative 0.53 is 0.58860, okay? And notice one thing about this is e to the x is always positive, okay? And of course, why this is, because again, if we raise to any power, the output is always positive. Then it's turned out that it is related to the exponential, natural exponential function. Then is the exponential function f of x equal to e to the x with the base e. It is often referred as the exponential function. Okay. Now you will see that again. Remember, e is actually is a number is 2.71882 raised to the power of x. Okay. So therefore, you will see that the function e to the x is actually is the function between 2 to the x and 3 to the x. And one thing about this is, again, the y-intercept is 1. Okay. Then now, look at this graph right here. Do you see that when x is less than 0, what happened to e to the x? E to the x is always in between 0 and 1. Okay. So then to this one here, when x is less than 0. And then now, what happened when x is greater than 0? When x is greater than 0, then you will see that e to the x, the output is always greater than 1. Okay? Then, of course, we know that e to the power of 0 is equal to 1 then. Okay. Based on this idea, then we can actually write any positive base b has a power of e, for example, namely b equal to e to the r. Okay. If b is greater than 1, then r is positive. Okay. If b is between 0 and 1, then r is negative. You could actually think of this as r values right here. Okay, so then now, how is this relate to the ab to the x? So we could actually write down the exponential function as f of x equal to ab to the x equal to a times e to the r raised to the power of x, because b equal to e to the r, or a times e to the rx. In this case, r is called the constant growth rate if r is greater than 0, and continuous decay rate if r is less than 0. Okay? Then we notice that when r is positive, that means r is increasing because b is greater than 1. If r is negative, then f is decreasing because, again, in this case, it's kind of like the b is between 0 and 1, right? It's decreasing. Okay, so now let us go to kind of like work with the vocabulary here. Okay, so if I have f of x equal to a times b to the x equal to a times 1 plus r to the x and equal to a times e to the kt. Now, in this case, I change the r to k, so I don't want to mess up with having two same r right here. Okay, so we know that a is the initial value, which is related to the y-intercept. B is what we call the growth factor when b is greater than 1, and decay factor when b is between 0 and 1. R is a growth rate when r is greater than 0, decay rate when r is less than 0. And then now, how about k? K is the one that relates to e to the kt. K is what we call the continuous growth rate if k is greater than 0. Continuous decay rate when k is less than 0. So here, this is the vocabulary that you should know. Okay, and in this case, if a is positive, r is positive, meaning the function is increasing. And don't forget that this is a right here. If a is positive, r is negative, then the function is decreasing. So again, this is my initial value here. Okay, so now I have another example to see how we actually sketch the function now. Okay, so suppose that we have f of x equal to e to the 0.2x. Okay, so to this one right here, again, I would like to learn the vocabulary that we are learning. Okay, so and remember we have f of x equal to a times b to the x equal to a times 1 plus r raised to the power of x equal to a times e to the kx, right? Okay. And now to this problem right here, we know that a, okay, and what is b, what is r, and what is k. I just want to see if we could actually identify this. Then, of course, right away, we know that a is equal to 5, and to this one, e to the 0.2x, right? So meaning what k is 0.2 then. Then now, what is b? Again, b basically is e to the 0.2, okay? And then what is R? R, it will be B minus 1, right? So therefore, it will be B minus 1. So it will be 2 to the point, e to the point 2 minus 1. Okay, so then let's see how we actually finish this problem. We know that the initial values, remember initial value basically is A. So therefore, I know that this is equal to 5. And then the continuous growth or decay rate. In this case, the K is positive, meaning what? This is actually is the growth rate, right? Continuous growth rate meaning is related to the K. And then in this case, K is equal to 0.2. Okay. And then now, to this one, of course, we will have, again, the growth factor. And then remember the growth factor is B, right? Like that. This would be B. Then in this case, B is e to the 0.2. Or if you use your calculator, you will find out that this is about 1.2214 then. And then, of course, the percent growth rate as well, right? So then in this case, then this is actually related to the R values. Okay. So, and of course, the R value is e to the 0.2 minus 1, or it is equal to 0.2214. And then my y-intercept is related to the A, the initial values. Okay, so now let us graph this. The function is increasing because K is positive, and then my initial value is 5, my y-intercept is 5. Okay, so now it is your turn, okay, to work on the next one then. Okay, so my initial value is 3. And of course, in this case, my K value is negative, meaning what? It will be the decay then. So the continuous decay rate will be negative 0.3. And then the decay factor, it will be e to the negative 0.3. And the percent decay rate will be e to the negative 0.3 minus 1. And of course, my y-intercept is 0.3. Okay. And then since the function is decreasing, y is decreasing again because the K value is negative. And then my initial value in this case right here is 3. Yeah, you got it? Okay, so now here is an example about continuously compounded interest. It's related to the exponential function. Okay. Now, continuous compound interest is calculated by the formula A of t is equal to P times e to the RT. Okay, so we say that because P times e to the RT is kind of like we have PERT, right? Per. So sometimes you will hear some of the students said that it's just per. P times e to the RT. Okay. Okay. Then what is the difference between the continuous compound interest and the regular compound interest? It actually is when we look at the problem. If you see that the problem states that you have compounded continuously, when you see this wording, then you know that you're going to work with this formula right here. If you have compounded monthly, weekly, daily, then you're using the regular compound interest formula. Okay, so therefore to this one, remember, we are going to use the A of t equal to per, right? P times e to the power t. Then to this one, we have P is, I'm sorry, 20,000. And then my interest rate is 5.25%. So it's 5. I'm sorry, is, and then we could use R is 0.0525. And then to this one, T is 10 years. Okay. Again, T must be in years. Okay. So therefore, again, to this problem, then I have P of T is 20,000 e to the 0.0525 times T. Then I have P of T, or P of 10 then. And the answer. Okay, so the last example is the example that we need to work with use a calculator to do this right now. After section 4.3, after we learn the trick, the log functions, after we learn the log functions, then we will be able to use the log function to try to solve this problem algebraically. Okay. Okay, so now to this one, it said that a population of bacteria is growing according to the equations. P of T equal to 1200 E raised to the power 0.17 T with T measured in years. We would like to estimate when the population will exceed 3,443. Okay, so then now let us try to graph the function to see what is going on. So in this case, I have this is T right here. This is the population of the bacteria, P of T. And then to this one right here, you know that to this one, we have P of T is 1200. What does this mean? It means that I have the initial value is 1200 here. Okay. And the bacteria is growing. It's increasing this way. With the continuous growth rate is 0.17, okay, which is 17%. And then now, what I would like to do is, I would like to know if I want to know that when the bacteria will go to 3,443. Okay, so we need to know that what is this time equal to. Okay, so therefore again, to the calculator, what you need to do is you need to set y1 is equal to 1200 e to the 0.17 t, and then your y2 is 3443 because again we would like to find the intersection point, right? Okay, so let's see how we do this then. Okay, so now then let us go to y1. Okay, now make sure that your port 1, 2, and 3 is not highlighted. What does this mean? This means that if you see a box like this, okay, what you need to do is you go arrow up and then try to clear the box. So put enter here. So you should have the port 1, 2, and 3 like this. Okay, and then now I'm going to input the 1200 second ln, right? E to the power of 0.17 x. Okay, and then put enter. And then the second one is we are using the 3443 then. Okay. Okay, now the first step is I will let you go to zoom and then select number 6. Okay, so this is actually the standard view, meaning in this case, you have negative 10 to 10, and this is negative 10 to 10. Now, you shouldn't see any graph because, again, you see that what we want to have is, we want to have the y-intercept is between 1200 and 3443, right? So what I'm going to do here is I would like to change my windows. Okay. I will increase my y maximum to 5000 to cover the two numbers, okay, 1200 and 3443. And then let's graph it again. Do you see that we have an intersection here? Now let us try to find the intersections. So how do we find the intersection? We use the second and trace. Okay. So to this one right here, then we choose number 5 to intersect, or you could just type punch 5. And then now usually I like to move the cursor closer to the intersection point. Okay. And then it will ask me 3 questions: first curve, second curve, and guess. So basically, you just need to put enter, enter, enter. Okay. So your answer is about 6.2, right? So and now you will see that the populations will exceed 3,443 in about 6.2 years. Okay. Okay, so that's it for today. Okay, thank you.